Greetings everybody and welcome back to another exam video. Today we're taking a look at the 2023 Methods Exam 2. I just managed to get my hands on a photocopy of this from one of the people in my CAS Programs Discord server, so if you're interested in joining the CAS Programs Discord server and getting some pretty cool CAS programs as well, then link in the description below. But yeah, I haven't taken a look at a single question in this exam, and apparently it's extremely difficult from what I've seen so far, so I might even get destroyed in this exam, I don't know. But yeah, I'll probably just do the multiple choice section first, and then do the extended response stuff in a separate video. Just so I can have a break if I need to run away from the exam. But yeah, question 1, the amplitude A period blah blah blah. So what's the amplitude? It's exactly 1/2. What's the period? Well, you just do 2 pi divided by the number in front of the x over there, which is 3. So it's 2 pi on 3. So looking at the answers, well, it's not going to be because amplitude's positive. So it has to be option E. Yeah, option E. So that's 1 mark there. Awesome. Question 2, the parabola with this equation, the equation of the axis of symmetry is, well, it's going to be at the x coordinates of the turning points. How do you calculate the turning points of a parabola? It's minus b over 2a, right? So that's like the part of the quadratic formula. So it's a minus, but what's b in this case? It's actually 2b, which is a bit confusing. So it's minus the coefficients in front of x divided by, a. The a is just the coefficients in front of x squared. So 2a there, the 2's cancel, so you get negative b on a, it seems. Yeah, negative b on a. Yeah, so option A. I should really do this in blue, not red, because I'm not marking anything. So option E. Okay, question 3. We have 2 functions, p and q, continuous on these domains. The domain of the sum is, domain of the sum, so that's just going to be the intersection of these two. So minus 2 to 3 looks like this, and negative 1 up to 5. So negative 1's exclusive actually. So we have negative 1 up to 5, which is over here. So what's the intersection? It's minus 1 to 3. So yeah, option E. Consider the system of simultaneous linear equations, the values of k, infinite solutions. We got the classic system solve. I'm so glad this question popped up actually. So we go to miscellaneous, we go to system solve, and then we have k times x. This works, by the way, because we only have 1 parameter, which is quite nice. So kx plus 5y equals k plus 5. I think that's the first equation. And then 4x, and then we have plus k plus 1y, k plus 1, and then times y equals 0. Future arguments, the parameters are k. So we want infinite solution, so it's going to be k equals negative 5. Awesome. If you want to do it without the programs, what you have to do is, I think, you have to find the gradients of both of these equations here, or both of these lines, make the gradients equal, and then try to make the 2 lines the same, because you want infinite solutions. Okay, question 5, which one of the following functions has a horizontal tangent? Horizontal tangent, so yeah, just like that, at 0, 0, so you want to pass through the origin. So x to the minus 1/3, well, I know what x to the 1/3 looks like, it's cubic, like that, cube root, sorry, like that. X to the 2/3, let's see, maybe if you don't know what these functions look like, which I don't know at the top of my head, let's just use the graphs page. So insert graphs page, and then we'll just plug all these in. So x to the minus 1/3, it has an asymptote at 0, so yeah, that's not going to work. And then we can try 2/3. So we go x, oops, it's not working, x to the 2/3. Does this work? Nope. And then we've got 4/3 and 3/4. So let's try those. So 3/4, nope, and 4/3, I think was the other one. 4 and 3. I think this might work over here. Looks like we have a horizontal tangent if we have, 4/3 there. Right, yeah, it should work, because if you take a look at the derivative of x to the 4 and 3. And then you evaluate this at 0 because this is still a positive power. You're going to get 0. So it should be E. Hopefully I got that one right. If not, that's embarrassing. Question 6, we have, I just realized I circled the wrong one. Oh dear, it's option D. we don't want 3/4. So question 6, we have integrals, and what do we want to do? We want to do 3 to 10. We want to find the value of the integral of 7 to 3. Okay, so first of all, they're oriented the wrong way. So what I'm going to do, flip them around. So this is 3 to 7 of f of x dx. But we want to rewrite it in terms of integral from 3 to 10 and 10 to 7. So what I'm kind of seeing here is this is the integral from, let's do 3 to 10 of f of x dx, and then minus the integral from 7 to 10 of f of x dx. Because if you go from 3 to 10, like so, and then you get rid of the integral from 7 to 10, you're left with the integral from 3 to 7, right? Yeah, so this is negative, this whole thing, by the way. So negative of this whole thing. So this is equal to, let's see, the integral from 3 to 10, that was c, so negative of c, and then minus the integral from 7 to 10, which is d. So that's d minus c, option D. Question 7, we have f of x, we have a log, and then this guy over here, some square root, the domain of the derivative. Interesting. So we have, because these are on the maximal domains, yeah, this is x less than, that's not the maximal domain, is it? Let's think about this. So we have log of x, so what's f of g of x? F of g of x is the logarithm of the square root of 1 minus x. All right. Because x is less than 1 over here, the range of this guy, so the range, is equal to, let's think about it, the square root of 1 minus x looks like this, right? Has an endpoint at 1. Okay, but because we're not including 1, that means the range is actually from 0 up to infinity, not including the 0. So the range of this guy is actually 0 to infinity, right? Yeah, that works out nicely because we plug this range into the logarithm. The logarithm is defined on 0 to infinity, so the range is just r. So option A. Okay. Question 8. A box contains n green, m red ball marbles, not marbles, balls. A ball is selected at random, its color is noted. The ball is then replaced in the box. In 8 such selections where n is not equal to m, what is the probability that a green ball is selected at least once? I did not understand the part of that question at all. Let me read that again. So the box contains n green, let's write this down, so n green, and m red marbles. A ball is selected at random, the color is noted, the ball is then replaced in the box. So we put it back in the box. So we're not changing the probabilities here, which means this is binomial. We can use the binomial distribution. We're doing 8 selections, okay. What is the probability that a green ball is selected at least once? So what we're going to do is we're going to let x be some kind of binomial. We'll figure out the parameters, count number of green balls that we see, or green selections whatsoever. So what's the probability we get a green ball? Well, it's going to be n over here, so the probability is n, and then divided by n plus m. How many selections are we doing? So trials, that's just going to be 8. So what do we want to do? We want to find the probability that a green ball is selected at least once, so greater than or equal to 1, but this is 1 minus the probability that x is equal to 0. Okay, but we can calculate that. This is 1 minus, we use the binomial formula. That's going to be, we do, well, some kinds of choose over here, but anything choose 0 is just 1, so we can forget about it. Then we have the probability of success, which is n over n plus m. We raise it to the number of successes, and then the complement of that, so m over n plus m, we raise it to, the number of failures, which is, in this case, going to be 8. So we get m over n plus m to the power of 8, and then we have this 1 minus at the front, so it's going to be option C, I think. Yeah, that should be it. Okay, looking good so far. Question 9. We have f of x is this piecewise buoy. The value of a for which f is continuous and smooth at x equals pi and 2 is... Okay, continuous and smooth. So what we can do, let me think. So what we can do is we can define maybe these two parts separately. So I'm going to define f1 of x to be equal to the tangent of x on 2. And I'm going to define f2 of x to be equal to sine of a times x. Okay. What do we want to do? We want smooth at x equals pi on 2. Right, so what we can do is we can... I'm going to try this over here. I'm going to define the derivatives as well. So define df1 of x to be equal to, we have a shift minus x of f1 of x, and I'm going to do the same thing for f2. So replace these with 2 over here. And I want to solve, first of all, I want the values to be the same at 2 pi. So f1 of 2 pi equals f2 of 2 pi. And I also want df1 of 2 pi to be equal to df2 of 2 pi. And I solve this for a. And I get something nasty, which is not good. Maybe we can guess, let's see. Well, the value of a can only be between, let's see, -2 and 2, it seems. Maybe if I put that restriction, -2 less than a less than 2, inclusive. Does that work? A equals -1/2. Okay, that's our answer. So yeah, first part, just make sure that we're continuous there, making sure the y values are equal, and the second part over here, just make sure we're smooth. And yeah, domain restriction. All right, question 10, continuous random variable has following PDF. Value of k such that this thing holds is... Okay, so what we can do is we can try integrate from 1 to 6 of this first part, and if the probability is greater than 0.35, we know the value of k must be between 1 and 6 somewhere. So let's do that. So we have integral, and we go integral from 1 to 6, was it? Yeah, 1 to 6 of, we have x minus 1 divided by 20, and then we have a dx. Okay, this is 5/8, this is 0.62. So because that's greater, I also want to check this 9 minus x thing as well. Let's do that, just to make sure the probabilities add up, even though they probably do. So 9 minus x over 12 instead. And then now I go from 6 all the way up to 9. Yeah, that should work. So because 0.35, let me think, because 0.35 is less than this 0.62 probability, we know the value of k must be between 1 and 6 somewhere. Right, so what I can do now is I can solve the integral from 1 up to k of this guy over here equal to 0.35 comma k. And k has to be positive, so it's 4 points, well, I approximated, but oops. So I can rewrite this as 35 over 100 if I want, yeah, exact values. And also I want such that k is greater than 0. Well, technically k has to be greater than 1, but yeah, same thing, doesn't really matter. So yeah, I think, yeah, root 14 plus 1 seems to be it. So go with option B. Question 11, we have a bunch of functions and the derivatives. The gradients of the graph of y equals f bloop 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 at x equals -2 is, so, well, what's dy and dx at x equals -2? It's just going to be f of -2 times g prime of -2 plus f prime of -2 and then g of -2. And this is going to be equal to, what's f of -2? That's -7 times g prime of -2. That's going to be 2. And then plus f prime of -2. That's going to be 3. And then g prime of -2. G of -2 is going to be 8. Hopefully I got that right. And that's -14 plus 24. So that's going to be 10. Awesome. 9 more questions to go for multiple choice. So we have probability mass function shown below. The maximum possible value for the mean of x is. Okay. Let's calculate the mean. So I'll use, let's go down to methods probability. We'll go to discrete info and I'll plug in the table. So -1, 0, 1, and 2. And then I'll go comma, and then we have k squared, comma, 3k, comma, k, comma, minus k squared. And then we have a minus 4k, and then we have a plus 1. So we have, this is the mean over here. That's good. Do we have any restrictions on k as well? Seems like k has to be greater than 0. Maximum possible value for the mean of x. So I have an expression for the mean of x. We have this. So I'm going to define this as e of x, or e of k, for instance. Right, so e of k has to be that guy over there. Let's see. So k has to be greater than 0. I'm concerned about this part over here because we also want negative k squared minus 4k plus 1 to be greater than 0 because it's a probability. I want to find some kind of domain for k. So I'm going to solve minus k squared minus 4k plus 1, and I want this to be greater than 0 with respect to k. So we have k between these two values. So we have an upper bound for k. So we know k has to be between 0 and this number over here. Okay, so what I can do is now I can use the analyze program because I basically want to find the maximum. I want to find the maximum of the function e of k I have over here, restricted to this interval. Actually, I'll redo this. So we want k greater than 0. Yeah, so we want to find the maximum of e of k restricted on this interval over here. So what we can do is we can use analyze. So analyze, where is it? Analyzed. And then I'll plug in e of k, comma 0 to, root 5, and then minus 2. And I think I'll approximate this. Oh no, we don't have to. So no stationary points found, but the start and the end points, that means the start and the end points must be the extremal values. So we have, that's no good. So we have root 5, maximum possible for the mean value of x. So we have the mean, k squared, so this value of 2 over here, this is k squared minus 4k plus 1. It has to be greater than 0, which means k has to be on this interval here. Okay, e of k is the mean that we just got. Here it is. And I want to find the maximum of this. What if I don't restrict? Maybe because I put this upper bound over here, maybe I shouldn't put that there. What if I just do analyze? Then local max is that, which is not good. Yeah, I don't know. Maybe I'll come back to this. I'll think about it later because I want to move on to question 13. So question 13, we have Newton's for loop. The return value of this function to Newton, we have 2 polynomials, really. Oh, because this is just a derivative, and then comma 1. What's 1? 1 is x0. X0. If df said x0 is the starting point, so it looks like that's fine. I'm just going to use my Newton's method program and see what on earth that gives us. So what I'm going to do is I'm going to go down to differential calculus, Newton's method, and then we have x cubed, and then plus 3x, and then minus 3, comma x, comma, and then we start at 1. Number of iterations, we have, I don't know, let's just go for 5. Let's see what that gives us. So we have the return value. So what are we doing over here? So I from 1 to 3. So it looks like we're doing 3 iterations. So 1, 2, 3. And that gives us return x0. So what's x0? It's the xn value, so 0.817732. That should be it. Let me just think about this program. So we have, each time we do this, so I from 1 to 3. So I is starting at 1, and then we only go up to 3. So we loop through this part over here 3 times, which means we update the x0 value 3 times. x0 starts at 1, right? And we're doing this update 3 times. So 1, 2, 3. So it's the 0.817732. Yeah. Okay. Question 14. A polynomial has the equation, this thing, the number of tangents to this curve that pass through the positive x-intercept is. So what we can do for this one is we can, the number of tangents to this curve that pass through the positive x-intercept. Let's graph it. I'll also define it. So I'll define f of x, or let's do p of x, to be equal to, we have x times 3x minus 1, x plus 3, and then we have x plus 1. Okay, I'll just take a look at the graphs page. So insert, then we have graphs, and then we have p of x. All right. Okay. So we want to pass through the positive x-intercept. I'm going to change the scale for this. I'm going to change this to, let's do negative 20. Hopefully that's better. And I'll change this to 20. Okay. So we want to pass through that point right over there on the right. So the question is, how many tangents can do that? All right. The number of tangents to this curve that pass through the positive x-intercept is, well, the first tangent that does this is the one that passes through the x-intercept itself, which is nice and straightforward. I don't think you're going to get any tangents over here that pass through it, but you will get a tangent somewhere down here where it kind of shoots up diagonally and passes through there. So that's a second tangent. And all the other tangents, I don't think, everything passed to the left over here, that's not going to pass through. So looks like you're going to get one right around here somewhere. And then moving up, you're actually going to get a second one over here as well, where it kind of points down into that positive x-intercept. And then, a third one on the actual x-intercept itself. So I'm going to go for 3. Question 15, x is a normal random variable with a mean of 100 standard deviation 20, y is a normal random variable with a mean of 80 standard deviation 10. Which of these following diagrams best represent the probability density functions for x and y plotted on the same set of axes? X is dotted, y is bolded. So x is mean of 100, so we want dotted to be more to the right than bolded. And we want the standard deviation of x is also greater. So we want the spread of x to be larger than the spread of y. I'm going to go for option A here. Because we want the dotted one, x is the dotted one, we want dotted one to be flatter because it has its highest standard deviation and more to the right. That's the only one where it's flatter and more to the right. So I'm going to go with option A. Question 16, let f of x be equal to this guy. Given that the product is this thing over here, the rule for the function g is, so we want e to the x minus 1 times something. Sorry, we want two functions to multiply to e to the, no, so f of x is e to the x minus 1, so that's f of x. We want to multiply by something over here to give us the product e to the x minus 1 squared. So what is e to the x minus 1 squared? It's e to the x squared minus 2x and then plus 1. We want x minus 1 here. Okay, so what do we need to, because we're multiplying, we're probably going to multiply by e to the something, right? Because all these are e's to the somethings. We want to, that's called the exponent of this part over here, e to the a. So essentially we will have x minus 1 plus a equal to x squared minus 2x plus 1. If you solve for a is equal to x squared minus 3x, and then plus 2, right? You can factor this into x minus 1, x minus 2. X minus 1, x minus 2. Is that right? Yeah, so it's going to be option B. Okay, question 17. A cylinder of height h and r is formed from a thin rectangular sheet of metal, length x, width y, cutting along the dashed line. Okay, so we have some kinds of cylinder. The volume for the cylinder in terms of x and y is given by. Okay. So what's the formula for the volume of a cylinder? It is, let me try to remember, it's pi times r squared times the height. The question is, what is r squared? And what is h? So the h is going to be, I think, yeah, it's going to be x minus something. It's going to be x minus 4r, because the height is only going to be this part when you fold it up. And then you have an r here and an r here, r here, r here. So you have h equals x minus 4r. Okay, now we just got to figure out what on earth r is, right? So r is equal to, how do we find r? Well, you can see this y over here. This y needs to wrap all the way around the circle, which means y is precisely the circumference of the circle of radius r. So we know y is equal to 2 pi times r. Yeah, y is 2 pi r. So rearranging, we have y divided by 2 pi is r, right? So v is equal to pi, r squared is y over 2 pi, but squared, h is x minus 4r, but what is 4r? It is going to be 2y over 2 pi. And now we just got to simplify that somehow. You could probably use the CAS to do this, but yeah, let's just do it by hand. So this is pi y squared over, actually that pi can cancel probably. So we have just a y squared at the top, and then divided by, that's going to be 4, and then just a single pi, I believe. Yeah, that should be right. And then this is multiplied. I'm going to rewrite x as 2 pi x over 2 pi, and then minus 2y over 2 pi. Actually, why on earth did I do that? Because the 2's are going to cancel. So 2 2's will cancel. So we have x pi minus y over pi. Okay, so this is going to give us, let's see, we have y squared, pi times x, minus y cubed, over 4 pi squared. So 4 pi squared, so C, B looks right, it's going to be option B, because we have a y squared pi x, minus 2y cubed. Well, actually, I'm missing a 2 somewhere. Oh dear. What's going on over here? So we have x minus 4r. What is 4r? 4r is equal to 4y over 2 pi, but that's equal to 2y over pi. Yeah, 2y over pi. I don't know why I wrote that extra 2 down there. So that should have stayed, and then we should just have 2y, and then 2y cubed. Option B. Okay. Question 18. Consider the function, okay, we have sine of a times x. The number of local minima in the graph of y equals f of x is always equal to. Okay. That's interesting, because if a is going to be some kind of dilation by factor of 1 over a, which is going in the complete opposite direction of the dilation happening on this interval. That's very interesting. So I feel like it's going to be either 2a or a squared. It has to be one of those, right? Or a, I don't know. Let's maybe just try a few examples. So we have define, well actually, we're going to solve local minima. So maybe we'll go to the graphs page, doc, and then we have inserts, a graphs page, and I'll graph out sine of let's go for 2x, sine of 2x, and we want to be on the interval minus 2 pi greater than x greater than 2 pi, or inclusive technically, but yeah, let's just do that. Let's just do inclusive. So local minimum, we have 1, 2, 3, 4. Okay, let's, we could probably make a line out of this actually. Let's change this to an A. We'll change this to an A, and we'll change this to an A. Create slider for A. So here we have, when A equals 1, we have 2. When A equals 2, we have, sorry, when A equals 1, we only have 1 minimum. When A equals 2, we have 4 minimums. A equals 3, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So it has to be, we'll just go with E, because none of the others will match that pattern. Okay, question 19. Find all values of k such that this equation has 2 real solutions for x, one positive, one negative. Okay. So I'm thinking of using the quadratic formula. That's just a quadratic. And then once I get the solutions for x, in order to test for one positive and one negative, what he actually wants is the product of the two solutions to be a negative number. Because if you have 2 negatives or 2 positives, then you're going to get a positive number for the product. So you want to solve for when that product is negative. So let's do that. I'll define, let's define q of x to be equal to, we have x squared plus 4, and then we have k plus 3, and then we have an x, and then we have a plus 4k. This is such an ugly equation. And then we have minus 9 and 4. So q of x. And what I'm going to do is I'm going to solve where q of x equals 0 with respect to x. And so we get 2 solutions as expected. And what I'm going to do is I'm going to define, let's do it as a1 is equal to this first solution over here. So grab all of that, and I'm going to define a2 equals the second solution, so I'm going to grab all of this stuff over here. Okay, and I'm just going to solve when a1 times a2 is greater than 0 with respect to k. So k is less than -3/4, or k is greater than 3/4. So it has to be option E. Option E. Last question, question 20. Let f of x be equal to this log boy thing. Let g of x be sine of x. Oh, this is reminding me of 2020 all over again. The largest interval for x were the values, x values for which f after g and g after f both exist is. Yikes. Okay, so sine of x goes from negative. That's so weird. Why do they choose? At least put a pi here or something. So let's see. So we go up to, what even is 5 in terms of, actually, let's do 2 pi. What is 2 pi? It's 6.28, so 5 is a bit less than that. So we have our sine graph here. It's going to stop slightly less than 2 pi. Right? Is it greater than 3 pi on 2? Yeah, it's greater than 3 pi on 2. So we actually pick up that minimum there. So here's our sine graph. This is g of x. And then we keep going to negative infinity, wherever that is. The largest interval for x are which values of f of g and g of f. So let's think about f of g first of all. So what is f of g of x? It's the logarithm, base e, of our g of x boy. So that's just going to be the sine function. So sine of x plus 1 over square root of 2. So when does that exist? The value largest interval of x. So x is going to be, so we can probably go up to 5 here. Well, actually, because log, we want this to be greater than 0. So when does sine of x plus 1 over root 2, when is that greater than 0? It's greater than 0 when sine of x is greater than negative 1 over root 2. So we want sine of x to be greater than negative 1 on root 2, which is probably around here. Okay, when does that occur? well, occurs for all these values over here. So what are those values? Well, this point over here, that's 5 pi and 4. This point over here, that's negative pi and 4. And you also got like negative, that's 3 pi and 4, I believe. But that's not, yeah, I don't think we need to worry about that. Okay, so if x is on this interval over here, then sine of x is greater than negative 1 over 2. That means this function is defined. Okay, so we have some kinds of candidate for the interval. Let's try to see if this also works for g of f of x. So what is g of f of x? G of f of x is, it's the sine of the logarithm of x plus 1 on root 2. Now sine has a particular domain, it has to be less than 5. Right, it has to be less than 5, which means we want this, the range of this log thing over here to also be less than 5. So let's see when that happens. I'm going to solve for when log of x plus 1 on square root of 2, when that is less than 5 with respect to x. And I got this over here, let's approximate. So if x, it looks like, if x is less than 147 or greater than this value, which is negative root 2 and 2, then we're fine. Okay, so we know that's, so for the first part over here, we know that's negative pi and 4 to 5 pi and 4, non-inclusive, because we require strict inequality over here. This is a possible candidate. But for the logarithm, so for this guy over here, we found the domain to be, well, this is negative 1 on root 2. Right? We have, I think we have inclusive. Can we have inclusive? I don't think so. Because this is, yeah, so this is negative 1 on root 2, comma, and then what of that value, which is 147. Right, so we need to take the intersection of these two intervals here. So it's going to be negative 1 on root 2, because negative 1 on root 2, I think this is greater than negative pi and 4. Let's just test that. Negative, oops, we have negative pi and 4. That's pi and 2. What am I doing? Negative pi and 4. That's 0.78. So this is greater. Root 2, negative root 2 and 2 is greater than negative pi and 4. So we're going to start at negative, yeah, this guy over here. Do we want that? No, it can be option A, right? Because this is exclusive. And we go up to 5 pi and 4. So I'm going to go with option A. We'll see if that's right or not. So I'm going to go back to that other question. It's been like 40 minutes or something. That's absolutely outrageous. I'm ridiculously slow at VCAA exams now. I'm so rusty at this. Okay, let's think about this even further, because I don't think I've put much thought into this. So the maximum possible value for the mean of x. Okay. So let's go back to that discrete info thing I did. So discrete info, we have k squared, let's make sure I put in everything, right? So negative 1, 0, 1, 2. We have k squared 3k, k, and then negative k squared minus 4k plus 1. And it says it's a valid distribution, so that's fine. Here's e of x. So what's e of k? It's going to be that. So that's the expected value in terms of k. Now I want to maximize this. So let's graph it. So dot 44. Let's graph e of x. Okay. So the maximum possible value. Well, just looking at this, if this is the expected value here, it's a negative quadratic, and k has to be greater than 0. Right? And because k is greater than 0, we're going to get the maximum at the vertical intercepts. Why did I not think about that before? That's actually fairly straightforward then. So just do e of 0 and it's true. We got it, it's true. Okay, so that's my multiple choice solutions. We'll see if that's right or not. I don't know if it's right. Someone else can check it, but I think it's right. So yeah, I'll go with that as my solution. So yeah, I'll take a break now. I need to eat food, drink water and whatnot. And I don't think I'm too scared of the exam yet. I won't take a look at these questions. I want to do it live so you guys can see what I kind of think about when I see these. It looks kind of scary though. Shouldn't be too bad though. So I'll take a break now and I'll do another recording later. Bye.